So hi, I'm Mike. I'm TAC, or Tactics, as it says up in my my little Dropbox thing there. I'm here to talk to you guys about functional programming. I'm talking all formally because we've got the camera going today, and I just like to draw attention to that at the start, just because it'll help me sort of start up. It's always hardest to start these things up. After you get going, though, I get really obnoxious with these. So what we want to do today is talk about functional programming. And I stayed up literally all night trying to figure out what I wanted to present today based on all the ideas that I had accumulated over the last 2 weeks. And I realized that I didn't know who was actually going to show up and what their level of experience was. Trying to write for an audience who I don't know who they are, it's kind of difficult. So I figured I would just go around and ask, what do you guys know about programming in general? And what have you heard, what do you know about functional programming? I'm just going to go down the line.
I know things like C and Java and Objective-C.
C, Java, Objective-C?
That kind of stuff. So
Okay.
nothing like functional programming.
All right. Cool. Yeah, so we got a couple object-oriented languages there, and then C, a good background in the systems language. All right. JavaScript and Lisp. So Lisp is obviously pretty functional there. It was Common Lisp, right?
Yeah.
Yes.
And Clojure.
Clojure coming up. Yeah, cool. Keep going around.
I've done stuff. Sorry, not to sneeze. Okay. Let's see. I've done some Arduino stuff.
Arduino, that's C, right?
It's like a offshoot of C, yeah.
Okay.
And some Python.
All right.
That's about it. A little bit.
Have you guys done Python at all? Python is usually, I think, a pretty popular language to start as a beginner. But again, I had no idea what people would know. So.
I did the Python class, and I'm working through the Yarn C++ book.
So more Python and C++? Cool. And then.
With a lot of primarily Bash and Perl and sysadmin side stuff.
Okay.
I support a Lisp application, so I do work with a lot of Lisp. Personally, I work with
So the sort of like the scripting languages, Perl and
mainly what I'm working with directly, yeah, but I'm supporting a Lisp application. I'm working with a lot of Lisp functions.
Okay.
And writing, templates in Lisp, calling various Lisp functions.
Mhm.
And also, a lot of the scripts that I wind up maintaining were written in a very functional style because they were written by the same people who they were writing the Lisp applications.
Right. And
I'm maintaining a lot of functionally written Perl.
I gotcha. Yeah, functional Perl. I actually don't know a lot of Perl. I imagine that that could be kind of tricky to do. And it is Common Lisp again, right?
Yeah, Common Lisp.
Right. That's
SPCL is the interpreter that we use.
okay. Cool. So it sounds like we've got a couple people who've done Lisp before. We've got Python and C, a lot of C derivatives, and a little bit of object-oriented programming as well. So functional programming, I spent a long time thinking of, functional programming is ... And I realized that I don't like that question. I think it's kind of stupid. If you were to define something like object-oriented programming, how would you do that? You can't necessarily give a nice, concise definition for what object-oriented programming is. Even something like procedural programming, you've got all these buzzwords, and the buzzwords are, they're culturally important, and they bring a lot of sort of an implicit understanding of what you are talking about. But they don't mean one definite thing. And so I wanted to try and sort of avoid giving a definition for functional programming and instead just go into some of the ideas that have made functional programming what it is and that are going to become, hopefully these ideas will bring it into more and more relevance as the future comes about. And so the first thing I want to talk about is immutable data. you guys have worked with, everyone has worked with a language either like C or Python, even Common Lisp. You're working with a lot of variables. And throughout the course of a program, the value of those variables will change. You'll say x equals 0, then x plus plus, and it increments x. Or you might have a user object, and you might start off with a blank user object and maybe a Python ORM, and you'll call a .load function and pass it a user ID, and it'll go off the database, and it'll come back, and it will fill that data structure with data that it grabs from the database. And so that would also constitute sort of a change in your variables, in your data. But I had sort of a riddle, which is if you have a problem with your computer, you call up tech support. You guys don't, because you guys just call each other. The average person calls up tech support. And what is the first piece of advice that tech support always gives you? Is it plugged in is the first one. What's the one immediately after that, assuming that it's plugged in? Turn it off and turn it back on. And why is that? Why do they ask you that?
Windows.
Because it's Windows. That's sort of a symptom of the problem. What would you say? It makes you feel like you're doing something. That probably in the course of what they're doing, I'm sure that's also very true. I heard you say the answer, but I want to hear your answer too.
Well, because then, like, if they like going on about their problem, then if they're restarting their computer, the person on the phone can look at the TV for what the actual problem is.
Again, that sort of ties in, and it's buying time. Those are all good, valid answers. The one for this talk that I want to select was, of course,
It resets everything to a default.
it resets everything to a default state. It clears your slate. It takes whatever weird, messed up configuration that your system got into, wipes it clean, and gives you back whatever it normally is when your computer boots, which in most cases is still good and is still valid to start running the program or to restart the hardware that broke or whatever it is that you were trying to do. And so that touches on the first claim that I want to make. Well, we're talking about state. We're talking about mutable state, that is, stuff that changes in your program. And I want to make a very bold claim. State is evil. You don't want to rely on state in your program. State is the number one reason that complexity gets into your program. It is just, from a formal perspective, it's one of the hardest things to reason about, but it doesn't feel that way to most people. Most people, when they learn programming, what they learn first is this sort of procedural, object-oriented would count under that style of programming where you create a variable and then you update it and you update it and update it and you finally get to a state where you want, and then user enters another command and it'll start changing again. But state is actually, when you think about it, when you're working with it, it can be kind of tricky to reason about. And I have a couple Python programs, and if you don't know Python, hopefully we can walk through just enough, and you can sort of pick up the syntax quick enough to sort of see what's going on here. I've got 3 functions here. And I think that's everything there. Yep. So we've got del every other, which, as the prompt says, it will go through your string and it will delete every other character in the string. So, for example, you could take hello and it would delete E and one of the L's, and that would be it, and you'd be left with HLO, I think is what it would be. Or you could take my name, Mike, and it would be MK. I want to delete or I guess in this case it actually deletes the even ones, so it would just be IE for Mike, and it would be ELO, I think, for hello. And the problem is this code doesn't work. What is it doing here? Let's just run through it real quick. So it takes your string, it's going to go through and break it up into a list of characters. We break it up into a list of characters so we can start manipulating the characters individually. And we're going to go from I equals 0 and walk through the indexes in the list, or in that list of characters. And if the index mod 2 is 0, which is just a programmer way of saying it's an even number, if you're at an even index, I want to delete that character. So then afterwards I should have a list that just contains the characters that I'm interested in, and I can just join them back together and return. So that seems pretty straightforward, right? But yeah, I said it with that sort of rising annotation, so you know it's not going to work. And I have to do some Python, and I want to do import as example. So example dot del every other. So let's do MIKE. In that case, it worked. What about hello? All right, so it's working pretty. Oh. Why did it work in that first case, not the second case?
It also wasn't every other in the first case.
Oh, that's a good point. That's why you write tests. I was actually surprised that one worked to begin with. I wrote this sort of a counterexample to using hello as my example. I didn't expect it to succeed in any regard, but it looks like in that case, yeah, it's deleting characters. It's deleting the correct number of characters, but it's deleting the wrong ones in the first case. And in the second case, we have this index error. Any ideas of what's wrong with this? This is sort of a warm-up. Hopefully it's not too much. If we don't want to think too hard too, I can just keep going on and go on with it. If you guys have a fighting chance if you're interested, though. So
Fourth character isn't there anymore because you deleted the second character.
yeah. So what's going on, and hopefully this will show up on the board. We're going to start up by breaking our string into an array, HELLO. And that array is mutable. We can change the values in it, which is great. We say I for, we're going to iterate over the length of the characters, so that's going to be, I is going to take the value 0, 1, what is this, length 5, so it's going to go 0, 1, 2, 3, 4, and stop just before 5. That's what the range function is going to do here. So when I is equal to 0, what's it going to do? It's going to say, well, I mod 2, I is an even number, and so we're going to delete the ith character. So we delete h. But then something funny happens. Because we delete our h here, these things, which used to be 0, 1, 2, 3, and 4, all of a sudden, because we've deleted that 0, we reindex things. We're left with only 3 elements in the list. Uh-oh. Well, then we go on to our second iteration. We go to L. We see that 1 is an odd number, so we skip that if. We go after to the next iteration of the loop. We have 2. 2 is an even number, so we delete 2 here. And we get rid of that, and then this 3 falls down to 2. We go to 3 now. I equals 3. 3 is an odd number. No harm done, we just skip it. I equals 4. Oh, now we're in a big bind. 4 is an even number, so it's going to hit that if statement, and it's going to delete the 4th element of the array. Our array only has 3 elements in it. Actually, this is going to be the 5th element of the array because you start at 0. So yeah, the code, if you're just glancing at it, doesn't seem like it should cause any real problems, but you know, we're deleting things sort of as we're blowing stuff up as we're trying to cross the bridge. Some analogy like that. We're trying to demolish a building while we're still standing inside of it. And so that's going to cause us some issues. And I want to make the claim that that's because the root issue, the root cause of this problem that we're having is that we're making this deletion. This deletion is a sort of a mutation to our variable. We're taking the variable and we're changing it, and that's what's causing our problem here. This next one is actually the more difficult one. I'm going to skip down to the last example here, the third one. Find smallest. Here we're going to take a list, just any old list, and And we're going to take, if it's a non-empty list, we need to have at least one element in it. We want to get the smallest element out of it. So we need to make sure, first of all, that the length isn't 0. Otherwise, we'll say, well, you didn't pass me the right input. We're going to throw an exception, panic. But assuming that there's at least one thing in it, we're going to sort the list to make sure that the smallest thing is at the bottom. And then we're going to return the 0th thing, which is the first thing, which, because we've sorted it, is the smallest. So what might be wrong with this code?
The list that have objects, but you sort objects.
That could be potentially a problem. That's definitely something that could be an issue, is that it might not be all numbers in there. If you have an array of people where you can't necessarily sort them, there's no compare operator, it would break. For the purpose of this, let's make the assumption that I did my documentation better. Let's just assume they're always going to be numbers, or at least objects that we can compare. But that is a very valid statement. If they're all numbers, what happens with this code? Does it look like it works? Again, these are all leading questions, so you know it's not gonna. So here's the trick then. We're testing it. A priori, we think that this probably does work, that there's probably no problem with this. And so we're going to do example.find smallest. Someone give me a list. 1, 2, 3. It's sort of a trivial list because it's already in order, but testing trivial things is a very important thing to do. If it doesn't work on the easy stuff, it can't possibly work on the hard stuff. So in this case, it gives us the right answer. Do maybe a different list. We can do 3, 2, 1. Is this going to work? Is this going to give me the right answer? It does. Oh, all right. We can actually try this 3, 1, 2. Oh, it's always giving me the right answer. Let's do something crazy. Let's have all 3 be the same number. Oh, it still works. I mean, it's kind of hard for it to fail in that case, I guess. But so this works, right? This would pass all of our tests. But I'm leading you on. That's what I love about these kinds of talks, is I didn't have time to come up with the one fishy example that actually did work to trick you. I thought about it. But in this case, so let's say our list is 3, 2, 1. So we do example.find smallest, and we pass an x. What's the smallest? What should be appearing from here? 1. Is that going to be 1? It's going to be 1. Oh, it works just fine. And then we just print our list out, and oh, our list changed on us. That's kind of weird. If you, pardon?
Like a sort rearranging.
Sort rearranges it. And again, in a similar fashion, we've taken our list and we've changed it. And in this case, it's even harder to figure out that there's a potential bug. And in the cases that we're just passing an object that has no other references, that you just pass that and then it's immediately garbage collected, there is no bug. There is no problem with this code. The potential bug is going to come in the cases where you have x or some other variable name and you save that object to a variable. Calling that function, the function returns the correct value, but it has some unintended side effects. Side effects are going to be an important sort of theme in functional programming world. This last one, I was actually inspired. I spent about 3 or 4 days learning the very, very basics of the new Mozilla Rust programming language. It has some cool ideas. It's kind of interesting. It's sort of a high-level language with no garbage collection. It's like a safe version of C++. So this is sort of like more what you might be doing with Arduino or with C, where you can pretend that this was written in C code. This isn't exactly a Pythonic way of doing things, but for the purposes of this talk, it's in Python, and that's what we're going to use. So the idea is we're going to have 2 lists of numbers. They're going to have to be the same length. You can think of them as 2 buffers that you can stack one on top of the other, and they're going to have sort of this shape to them. We can even put hello in both of them, because I like the word hello in my examples. Let's not use hello and hello. Let's use hello and good B. The B stands for bye. And so what does this do? We give it 2 lists here. and then we pass it in a number, and it's going to take the first list. In this case, yeah, I guess this would still work. Again, I'm sort of making the assumption here, because it's padding it with zeros, I'm sort of making the assumption that it's a list of integers. Python, it's not going to matter. So we're just going to use hello and good D for the time being. But what we want to do is shift over the first list and sort of copy it into the second list. We shift it over by the amount n. So let's just pretend that n equals 1. What this should do is it turns that into a 0. And then it prints out HELL, and then the last byte is sort of truncated off. It's sort of a shifting operation. You'd see this kind of thing a lot if you're working with low-level code with Arduinos or Raspberry Pis, where you're working with bit twiddling a lot, or working with buffers. This sort of, like, I have 2 buffers and I need to copy them, but I need to, like, sort of change the second buffer. It's sort of a common operation that you would see. And so this code is pretty, it's a little less clear than the one. This is the padding operation. That's what this last comment here is. The remaining slots are padded with zeros. So we pad those. We pad the first n slots. And then for the remaining slots, we're going to take whatever's in A, starting at I, and then we're going to insert it into I plus whatever that last index was. So great kind of problem that you would see in sort of an algorithms class if you were to take one of those. But let's see what happens here. Example.copy shift. We do 1, 2, 3. Let's do 4, 5, 6. They have to be the same length. And I also have to pass a parameter. Let's say I want to shift this by 1. So here we would expect to see 0 in that slot, and then 1 and 2. Right? Is that what we get? Oh. And here I've even messed up my example. What it's actually doing, it's not going to return a result. This doesn't actually return anything. This is modifying one of the lists. That's... Pardon? You may want to print it. Usually in something like C, what you would want to do is you'd want to set these in variables to begin with. 1, 2, 3, and then y equals 4, 5, 6. And then you can do, rather than having these like just passed in directly, you pass them in like that. Now it updates our variables. X stays the same. Y, though, we take this, we shift it over 1, copy it, and we pad the remaining empty slot with 0. If we wanted to do that with a shift of 2, it takes our 1, 2, 3, it shifts it over 2, so only the 1 remains, puts it down at the bottom, and then pads with 2 zeros. And this is another really tricky case where if you try this with all the different inputs you could possibly think of using these x and y variables, it'll work. But there's still a bug in it, and it's really kind of hard to spot. Now, there's nothing wrong with this logic if you have that you're filling the padding in, and then you just copy the one array to the other array. You're not changing the first array at all. You're not messing with the length of things. It's very cut and dry. But there's one teeny tiny, very hard to spot problem with it. If you guys want a second, I'll give it a chance. That would be a possibility. That's not the possibility I'm thinking of. Definitely, if you had specified an n that was greater than the end of the list, that would give you not a buffer overflow in this case. If it were C, that would be a potential vulnerability. In this case, it throws an exception. That would be a potential error. Again, it's not the one I'm thinking of, but it's a good idea to keep out. It's good to keep an eye out for those sorts of things. And so the problem that we're going to have with this one, if you guys are done staring at it. Yeah, okay. It's like, this isn't the most interesting example, but it's So if we have x equals 1, 2, 3, and y equals 1, 2, 3, that's going to work just the same as anything else, right? So we have x is 1, 2, 3, and then y is padded over. So if you pass the same value into both slots, it works. The one place where it's going to fail is where you not only pass the same value, but you pass the same object in twice. And here we have x equals 0, 0. Whoa, x wasn't supposed to change. Y has the correct value, but you've now clobbered x somehow. And you would never know this through usual testing means. This is a very hard bug to spot. And if you in these contrived simple examples where you know that I'm showing you a 30-line Python file, they're easy to spot. They're easy to track down. Even when you're debugging, they may not be hard to track down every time, but the times that they are hard to track down when it was in someone else's code that you wrote, or you weren't expecting it, or your mind is thinking that, oh, it's probably I'm dealing with a library that I'm not familiar with, or I have this other concern, I'm working on this algorithmic code, and I have to keep this in my head while I try and debug this sort of side project, this yak shaving exercise, and all of a sudden you will forget to check these things. These are hard to spot bugs. You wouldn't know them from looking at your code. And so all these are examples of problems with code that come about when you have side effects in your language, when you're relying on mutable state to do what you want to do. So, state is evil, and I hope that was a good exercise. That was what I figured out. It was my epiphany at, I think, 5 a.m. this morning. There is one counterpoint to this, which is that state is probably the most evil thing from a reasoning about code perspective. The problem is that mutating variables is also the most useful thing you can do with a computer. When you're working with an Arduino or a Raspberry Pi, you want to be able to send I/O out to your pins and be able to change things on your breadboard. You want to be able to light up LEDs. If you're writing server-side software, you want to be able to talk to the WebSocket. You want to be able to send messages to your client. You want to be able to read and write from the database. Those are all side-affecting operations. They all suffer from the same sorts of problems as these examples did. Maybe not to the same degree. Maybe the libraries are a little cleaner, and maybe the modern languages and the best practices mitigate those to some degree, but there's still potential pitfalls. Every once in a while, having it be an even rarer problem than what you expect makes it all that much harder to find when it does happen, because it catches you off guard. C programmers don't have such a problem with this because they're used to seeing that problem. That last example is a problem called aliasing, where even though it looks like you have two objects, they're actually the same objects. It's like what happens when you invite your grandmother and your what was the relationship? Your godmother, your grandmother and your godmother over for dinner, but it turns out that your grandmother is your godmother, and so you only have dinner for her. But you still invited the two people. You sent out two invitations. They just went to the same address. Those sorts of things happen in programming more often than you would expect. So the point here is that we have a conflict. We have state is hard to reason about in certain corner cases. State is very useful. How do we reconcile those two problems? And here's where I'm going to remind you of some lessons that you learned when you first started programming. I'm pretty sure most people have heard it. I was trying to gauge, because I learned this. I learned these lessons, and I think the couple of people who I talked to had also learned these lessons, which is, how do we feel about global variables? Everyone knows this one, right? Sparingly. It's the liberal way of putting it. Definitely sparingly.
Their global variables are variables that are defined for the whole program and not within a subroutine. I'm not sure.
Yeah, so they're viewable from a very large portion of the source code. Sometimes, in most cases, they're viewable everywhere in the entire application. You can see them absolutely everywhere in your program.
Use them for everything, right?
Use them for everything. We have the embedded systems, the real-time kernel guy. C programmers, in general, just out of nature, tend to use a lot of global variables. Systems programmers, and when I say that, I mean people who work on, let's say, websites or very large-scale infrastructures, tend to try and ban the practice entirely, where it's totally not allowed. And there's a spectrum there. There's a nice middle ground, which was try not to use them. That's the one that I probably fall into. It's a tool. It's a dangerous tool, but sometimes you need a dangerous tool, or sometimes you're just really lazy, and the dangerous tool is the nearest thing that can get your can of beer open. So the other thing, so that was advice known long ago, before the invention of object-oriented programming. That was back when C was first invented in 1970. I don't know the exact date. In the 1970s, they knew this was an important thing to do. Avoid using a lot of global states. And the other thing that sort of developed out of this, that sort of is a change from how things used to be done in assembly, are, you had mentioned subroutines. Most languages have a notion of a function or a method, and almost every language works virtually the same in this regard. You have the name of the function, a bunch of variables, and then you open it up, and then maybe there's a couple more variables that are introduced with some keyword, maybe var, A, B, C, and then you do your function. And these guys here and these guys here are local to that function. They are limited in scope. You can't see them from outside of the world. And that helps you prevent mutability. Those things will only exist for a short period of time, and they're not accessible to people who shouldn't have access to them. It sort of prevent people from mutating things by not even letting them know it exists in the first place. And then around, I have the exact date here. When was C++ released? It's 1980 something. 1983, I think. I don't have that. I threw it down in my notes somewhere. When C++ took off, all of a sudden the big thing was object-oriented programming. Object-oriented programming was something that existed for, I think, half a decade earlier. It was I knew the name. I did all this research, but I haven't slept. So Smalltalk was one of the first successful languages that invented it. The first one was, I can't remember. I wrote it down. It's not Agol. Anyway, so C++ though was the big trendsetter in object-oriented programming. Everyone started using classes. Everyone started talking about methods rather than functions, and classes rather than structures. And we got these funny keywords. We had private, public. There's also internal. I think it's what it's protected. Protected. I don't use a lot of C++, but I used it back in my youth. And these things, these three keywords confused the heck out of me when I was first learning programming, because I didn't understand what they were for. And it was only after a long while in programming I started to appreciate what they're there for. They serve the same purpose as putting variables in their little function boxes. These put variables in class boxes. It prevents people from outside of the class in the case of protected or public. In the case of private and protected, it keeps people from outside of the class from accessing your internals. It keeps your privates private. In addition to that, you also had this idea that you should never access member variables directly. You should always go through some sort of a getter and setter. It has led to the most horrific abundance of Java-inspired boilerplate in the world, where not only do you have to write the one line for the field, you also write two lines, one to get it and one to set it, with the sort of fantasy promise that at some point you may want to change those, but in like 99% of the cases you don't actually want to change it. But if you didn't have that and you compiled it against your code, there's a reason that you write getters and setters. It's not a good reason, and Java should be ashamed. C# does it right. Python, Ruby, JavaScript all have sort of the ability to make a function look like a member variable. There's ways of tricking the compiler and not caring with those languages. So the whole idea behind object-oriented programming is these three keywords probably are the most central piece of it. You want to keep your private pieces private. You want to hide your moving parts. You want to hide your state from the rest of the world. Encapsulation is the fancy term for it. What the ideal was in Smalltalk is you would have a bunch of objects that were sort of these self-regulating agents in your program. and they would pass messages back and forth to each other. And it was only through those messages that you would be able to communicate what you're trying to do. You get a message, you can work with your private stuff in the privacy of your own little class, and then you send another message out. And it works pretty decent in practice. It's been adopted by every major business doing large-scale systems programming. Functional programming goes a step further than that. Rather than having your moving parts encapsulated and protected, it simply does away with the moving parts. What if instead of having your mutable data hidden behind a door, you just didn't work with as much mutable data? What if you decided, as a default, you always reached for immutable data? What would be the consequence of that? That's what the first big idea of functional programming is. Immutability, there are differences between Lisp and the closures of the world, the MLs and the Haskells, the Erlangs and the Scalas. They all share one really important theme, and I think this is probably the most important theme, and something you can take home to any language. See what you can take in your program that's changing and keep it static. Because I wasn't able to learn PowerPoint in the week that I had to prepare this presentation, I was going to have a really fun picture. Wait, I can still do this because I have my notes right in front of me. Where did I put them? It's like, now I lost them. I've deleted part of my notes. There is unfortunately a disconnect here. I was going to have a picture of two different styles of mousetrap. One that has a spring and a piece of cheese and a little lever, and when the mouse presses on it, it dies right away. And then the other kind, which was a playground with a guy on a diving board and a little chain here, and I think there's a marble that spins around. I think Milton Bradley or some other company used to make this as a game, and you went around the board. Which one of those is the more trustworthy mousetrap? Which one would you trust to get the job done? And you trust the piece of wood with the friggin', it's got one moving part. Is it broken? You check you check the spring, you check the trigger. If those two things are working, the mouse is probably not going to have a good day. With the other one, there's a lot more room for it to break. And that's the whole idea behind functional programming. If there's fewer moving parts, it won't break. Same thing with solid state drives versus hard disk drives. Even though the solid state ones have a shorter shelf life, if you drop the two of them, it's more likely that the solid state drive will survive because there's fewer moving parts to break. Do not have moving parts. How can you reconcile that, though? You have all this moving stuff. You're so used to. Every C programmer, anyone who learns C knows how to do this. For int I equals 0, I is less than length, I plus plus. You just sort of memorize this. Same thing if you're doing, pardon? Length minus when you want to start, I use the less than. I've always learned it this way. You could also do it that way. You have to have your mantra, though, and you always do it the same way. It becomes a habit. It's sort of this memorized pattern. But this inherently has a mutable variable in it. We're changing I at every iteration. And we saw how even when we're doing something in fancy Python, it can still be an issue when you're changing things. So I have lost my place. What good is immutable data if our basic tools of programming are all based around changing things? And that's really the hard selling point to functional programming. It requires you to think about your problem in a different way. To a large degree, it almost requires a different set of tools. People have tried to implement these ideas into other languages like Python, Java, C++, and they work to some degree. But the tools are really optimized for languages that have them built in from the start. Your Scalas, your Clojures, your Haskells, your MLs, your F-sharps, those sorts of things. So to start off, to sort of give you an idea of what this perspective is all about, when we're programming, a lot of our programs have to do with data. What kind of data? It could be business data. In that case, you're working with your sales data, your historical trends, your customer database. You have the science world where you're dealing with measurements of all different kinds. You have the temperature of the solar system, the microwave background radiation, quantum stuff going on here and there. You've got all sorts of genetic information. There's just tons and tons of information going around in the scientific community. It's all data. It's all numbers. It's all there to be processed. Any sort of statistics, machine learning, data mining. If you're trying to be Google, you need to be very good at organizing your data. If you're smaller and you want to be as successful as, maybe not as successful as Google, if you want to be successful as the largest company in Chicago, you need to have some understanding of how to process data, how to work with it. And then even on a smaller scale, let's say you don't care anything about business. You want to be the lead hacker. You want to join the open source community and work on the Python compiler or the GNU C compiler or Clang or something like that. Compilers take data in the form of programs. Your program is then the data that you send through a pipeline. Your program goes in one way and it comes out as assembly code on the other end, or LLVM in this world nowadays. So with data, there's one big rule with data that they especially adhere to in the scientific community. Once you have data, once you've published it, you don't try and change it. You don't go to the publisher and say, no. We actually meant to change these 3 values over here, and we'll just get rid of this data over here. That's not what we meant to publish. You don't do that in the science world. And I would like for that to sort of spread out to other areas as well, and to other degrees. In the other realms, you can do that to varying degrees. Compilers are also very good with, you didn't like that program you got? Well, just recompile it. That's another case where you throw away data and create new data. You don't change the data once you have it. And then machine learning, again, Google's scraping all this data. It will keep some sort of history of the websites, but at the end of the day, it's not going to go back and change what it's already scraped, because it could just scrape more data. Why would you go back messing with stuff that you've already picked up when you could just go get some more? We live in a world of data nowadays. And so here is where we get to the functional and functional programming. If we can't change the data, what can we do with it? And I sort of hinted at it a little bit. We can't change data, we produce more of it. We take input data and we perform transformations on it and produce output data. It doesn't overwrite the data that was already there. It's new data, it's derived data, but it comes from, it's sort of separate in its own little world. One good example of this is the Linux file system has been doing this for a number of years, and I think I had an example. Every time I go look at the bottom of this, I'm disappointed because I have deleted all my old notes. So you have the Unix pipe operator, and if you want to grep something, I do this all the time. This is just the example that I use. People will use other examples. You can do something like tail, you do n 10,000 or something like that to get the last 10,000 lines of a file, and then use the pipe operator, and you grep it. And you want to grep it for error because you want to know where your errors are. But grepping all of the errors is too much. You want to get rid of everything that's, let's say, your word processor. Everything that says, let's say, I don't know, MS Word, because that's totally a Linux product. If you have MS Word in your error log, you definitely don't want that on your Linux file system. You use the -v flag to remove it. And then, because you want these things all grouped together, so you can see the frequency of the errors, let's say, you can do sort. And this will give you a sorted list of all your errors, and you can then, there's other commands that I'm not so familiar with, where you can combine those to see. Unique-C. We have someone who actually knows some shells. I should have asked you to help me prepare this talk. And you can get a count of how many, like a histogram of all the different errors you have in your system. You can see which ones are most frequent, which is kind of cool. But some things to note here is that tailn produces some data. grep will consume some data and then produce more data out the other end of the pipe. It doesn't actually alter the data that's coming in. It just basically throws it away. But it sends more data out. And then it goes down the pipeline, and it goes to another grep, which will do something slightly different. It takes the data in, transforms it, sends new data out and throws the old stuff away. Sort takes the data in, sorts it, throws the sorted data over there, and then the original stream just thrown away. And then finally you get to your sync, it'll print out the unique count, and then it comes to your screen by the default action. It's not being piped anywhere else, so it ends up in your standard out. So this is sort of functional programming in the Linux world. This has been around for a number of years. This has been sort of the backbone of a lot of, I mean, you probably know this better than me. You should be. That's how you do everything. And it gets dumped to Postgres in the end of it all. So what I want to talk about here is functions in particular. We have these functions which are doing these transformations. And in the Python, we had some that were doing this other stuff as well as just returning output. I want to separate the world into two. I'm going to separate the world into a Venn diagram. The teeny tiny overlap in the middle. And this is a general statement. It doesn't apply in all cases. It probably doesn't apply in all programming languages, but this is mostly the way it goes. You have functions, the world of functions. And over here you have functions that take input and produce output as their primary purpose in life. They take input, produce output. Over here you have functions that take input, but then instead of having output in the form of a return variable, it does something. Whoa! This is a side effect. The side effect is sort of this catch-all term. It could mean writing to a variable, altering any sort of mutation. It could also mean writing to a disk, reading from a disk, any sort of operation that affects the world. There's a famous, one of the authors of Haskell, the GHC Haskell compiler, Simon Peyton Jones, likes to use the analogy launch missiles. Because side effects, even though they're often mundane and boring, in some cases it's known that side effects can have very devastating causes. And so the most extreme one that he likes to use in his examples is launch missiles. If you've launched missiles, you can't take them back. In the case that you have input and a side effect, it's very common for there to be no output at all. The canonical example of this is the print statement, or printf, or any kind of print in any language, where it takes input, it prints it out to the screen, but then it returns void, or nothing, or doesn't do anything, or returns none, or just kind of the function ends without using the return keyword at all. You've got a little bit of overlap, and these are if you ever see something in the middle here, like this is sort of the functional programming world. This is sort of the imperative world. The imperative world uses both circles. Try to avoid ever having a function that does both at once. That gets kind of confusing. But the functional programming world really wants to prefer everything on this side of the Venn diagram. Your inputs, your outputs, no side effects. And what you get there is this miraculous thing. Is like the greatest blessing a programmer could have. One who's frustrated at their jobs that they've spent too much time debugging legacy code that's just awful. Which is you get something called referential transparency, which is a fancy word for saying it doesn't matter how many times I call this function. I can call it once, I can call it 100 times. It doesn't matter when I call this function. I could call it before this system call, I could call it after the system call. I could call it both before and after by the last claim. It also doesn't matter what other threads are executing at the same time. I can have this one executing over here, and this thread can do whatever it wants. But because I only look at my inputs, which are by definition private, and we're making the assumption here, I guess I should make this claim. Here, what you really want is for these to be immutable. If you have immutable inputs coming in, and then immutable outputs going out, then you have what's called a pure function. Pure, I like to put it in quotes, because pure, well, I don't want to get into that too much, but there's different levels of purity. For our purposes, this is pretty good. And so a pure function, the word I used before, if you guys want to look it up, if you can read my handwriting, referentially transparent, which is just the most ideal property in the world to have. So one thing, I can draw this Venn diagram, but I think it probably helps to have some examples here too. I can just throw these onto the board. These guys here. So where do these guys fall in the Venn diagram? And this is again Python, if you're not familiar with Python. I sort of give you the answers. Sort modifies its list, and it doesn't return anything. So that is strictly over here. We have sorts over there. What if we take the length of a list? It's a function. It's a pure function. If we have l.append, if we're adding something to the end of the list, we're mutating it, and we're also not returning anything. Remove, this is the other way around. When you see these sorts of pairs of functions, add, remove, push, pop, init, dinit, malloc, free, new, delete. Programming things like to come in pairs, which is why, if anyone asks, the stack data structure is actually the most important data structure, not the queue. That is my personal opinion. Making sure that things are paired is something you can do with a stack. So these guys are sort of opposites of each other. Pop there. Pop is kind of a funny one. It removes the last element of the list and returns it. So that'll actually belong in the middle. That's one of the few exceptions where I think that's an acceptable thing to do, just because it's so ubiquitous to be able to push something or pop it, and when you pop it, get the value back immediately. Sorted is a Python function that came about only a couple of years ago, I think in 2.7, I think it was. 2.6, something like that. Maybe a little bit earlier than that. Back when I first started learning Python, which is a while ago by now. Sorted is actually sort of a functional version of sort. Sort of. It will not modify the list, but it will return a copy of the list that is a sorted version of that list. And then we discuss, and so that's over in functional land. And then print, like I had mentioned, that's the sort of poster child of side effects. You give it something and it does something and it doesn't return any results. And in fact, in Python 2, that's not even a function, it's a keyword. It doesn't return anything at all because it's not an expression. They changed that in Python 3. So pure functions. I already ranted about that. So yeah, I guess I should say this. I didn't want to have to bring this up, but I'm going to. Functional programming, function. Why do we call it functional programming? Because we use this term. Function is actually a word that comes from scary math land. And in scary math land, a function is simply a rule that assigns outputs to inputs. It's a machine that transforms inputs to outputs, if you want to say it in like more forward direction. Nothing more than that. These functions are a little more generalized. In programming, you can have functions that throw exceptions sometimes or get stuck in infinite loops. They don't return values. But by and large, these functions in functional programming, the ones that we're interested in, are much closer to their idealized mathematical counterparts. You guys don't care about math, probably. Some of us do. For anyone who may be watching at home, what's important to take away from the mathematical roots of functional programming is this. When you have a mathematical understanding of your language as a mathematical object, as a mathematical system, you can perform optimizations on your code that you wouldn't be able to do so with confidence otherwise. There's an entire industry in academia around designing programming languages with certain properties that are based on these and often using certain type systems that guarantee that certain kinds of transformations can be performed and done so in a way that won't mess up your code. Assuming their implementation is correct. That's always like the big asterisk there. But their ideas are sound, and you can do some really, really cool optimizations in these languages that you can't do in most other languages. So, now that I've brought up the scary math word. We're going to talk about functions some more. Functional programming. A lot of people get introduced to functional programming through this weird construct, and it's sort of like the oddball out. People originally, I guess, about 10 years ago, like only maybe half of the programming world knew what these were. Nowadays, everyone wants these things, and they are lambdas. You want lambdas in your programming language. Just a quick show of hands. How many people have heard of lambda before? We got the functional programmers. No lambdas, no lambda, no lambda. So a lambda is a way of defining functions. Say, pardon? Yeah. It's okay. I guess we got we also got the capital variant. Although this one is sort of yes. We got Half-Life and we've got Stargate, respectively. You can't actually study capital lambda until you graduate from lowercase lambda, and I'm not even like joking about that. We'll study something called System F after the lambda calculus. We're not going to be doing that, but so lambda. Here I want to switch. I was using Python before. Python I thought would be a very familiar language for a lot of people. Python suffers from a case of really bad lambda support. And it's kind of unfortunate, and it was sort of intentional, and I'm not sure exactly if people feel the same way about it nowadays, if that same decision would be made. But we're going to switch to Node JavaScript that I installed for just this purpose. So we can define a function like this. The most important function you're going to see all day, at least contrived examples, double, which we can do double 5, and it's going to give us the result 10. Sort of. You can almost see that, the light gray here. 5 plus 5 is 10. All right, that's not very exciting. What you can do, though, in a language that supports lambdas, is I don't have to declare that function and give it the name double. I could, for example, in parentheses, say function x, return x plus x, semicolon, and then pass it 5. And what this is going to do, you can see that we've actually removed the name from the function, making it anonymous. This function is going to be an object in the program. We're not going to give it a name. We don't need to. It's not going to be something we keep around. We just want to use it for the one-time use. We evaluate it, and if you squint and you're not too bad on the color, you see it returns the same value, 10. Is that great? Awesome. Should I go turn it back on? So here we got another function, iterate. This is sort of a mathy function. It's not doing anything too interesting. But this is an interesting thing that demonstrates what you can do with functions in these languages. Functions are actually objects in the first class sense. You can pass them as parameters. You can return them as results. Here we're going to see how you can pass one as a parameter. N is sort of understood to be an integer. F is going to be a function, and X is going to be some object that function can act on. And aside from the funny way that my cut and paste decided to post this in, what it's going to do is it's going to repeat that F n times and apply it to X. So this is easier to explain with an example rather than just saying it. So iterate, we can do iterate. We iterate 0 times, we pass it double, and we give it the initial value 1. It calls f 0 times on it. If we call this with 1, it will double that number because it will apply that function once. If we apply double twice, what we're going to get, and this is a technique called recursion. You can see that the function is defined in terms of itself. It's par for the course in functional programming. It's sort of this alternative way to do for loops. It has its own little mind-bendy ways of working. It's kind of an interesting thing to learn about. It's how mathematicians do it. Don't worry about this. Usually you don't have to work with explicit recursion. Not all the time. Sometimes you do, and you would need to know it for functional programming. But we're just going to pretend like you already understand that. You call iterate twice, and it'll give us double 1. It doubles the 1 to give us 2, and then it doubles that to give us 4. And as we do this with higher and higher values, we'll see it's going to give us powers of 2, because double, double, double of 1 will give us 2 times 2 times 2 times 1, which is 8, 16, 32, and all that. But the important thing to note here is that we're passing double as a function to our function. And that's what's great about functional programming, is it's like this whole meta thing. It's like, yo dog, I heard you like functions, so I'll let you pass functions to your function, so you can call functions while you're recursing through your function, while you recurse through your function, while you recurse through your function. And not only can you pass functions like this, that lambda syntax, which seemed kind of artificial and like, why would I use this? It's often handy to have something where you just have a one-off throwaway function. I can define it directly like that. Had I not defined double above, because that wastes a valuable name, I could just pass that function directly, anonymously, as that, and I could get the same result. There's one other example that I had for this. This does use mutable state. This is something that you would probably see more in like a Lisp. This technique I think first learned it through Scheme. Famous make counter example. This is interesting because it's a function. It defines a local variable, and then it's going to return a function. It's going to return a function itself. It's a function that returns a function rather than a function that takes a function. And in this case, there's also one other really interesting property about this. The function is nested. What variables are available to it? If it had any parameters, it would have its own parameters available. This one does not. If it had any locals, its locals would be available to it. It doesn't have any locals, so don't worry about that. But yet we still use a variable. Where does this variable come from? It comes from the function that it's nested inside of. And this is a technique, a phenomenon called closure. You're closing over what's called the free variable in the outer scope. If you've ever worked in Python, I think it's Python 3 only supports this. I don't remember if it was in 2. The non-local keyword allows you to declare variables from the outside world, from outer scopes, and bring them inside. And this has some really interesting behavior. It's sort of non-intuitive at first. And I just want to sort of expose you to the idea if you haven't seen this before. But we can do var c equals make counter. Now, what is c here? C is a function. Well, let's call it. How many parameters does it take? Well, when we look at what's being returned, because we called make counter, it's returning a function that takes 0 variables. So we just pass it with an empty parameter list, and it's going to return what? It's going to add 1 to the counter, which is 0. That makes sense. So it returns 1. Okay. The cool thing about this is this counter variable lives on in memory. It is closed over inside that variable c. That c sort of has a reference to that counter variable. And so if I call this c over and over and over and over again, it's counting up. That variable is counting up. And this is sort of I don't want to say necessarily a poor man's way to do it. This is an alternative way to do encapsulation. If you work in JavaScript, this sort of thing becomes second nature because you don't have a public and private distinction there, and people love their anonymous functions in JavaScript. And classes, there's no classes either. It's because classes are really defined as a function, which is very weird to me still with the prototype paradigm that they use. But this sort of technique is used all the time in JavaScript. So what are these things actually good for? You have callbacks is probably the number one primary thing that, especially in JavaScript, just loves their callbacks. You have any sort of AJAX, what you do is you send information, but when you make the send call, you'll pass it a function in the same sense as we had above, where you're passing a function here, usually an anonymous one. And then the server gets that message, that AJAX call, and will send a response back. What happens when you get that response back? It's asynchronous, so your program can't wait for it. What it does is it calls the callback that you sent it. It will call the function that you told it to call. It's sort of like, it's very similar to when you get a bill in the mail. If people still do, I don't like using the online wireless bill pay stuff. Not quite there yet. I can barely get my computer monitor to work or my Wi-Fi to work. But yet I'm a programmer. when they send you a paper bill, they'll send you an address or an envelope inside of that bill, and then the bill itself will have the return address on it. So not only do they send you how much you owe, but they also give you a means to return it to them in the proper way that they can find it and categorize it and classify it. And that's exactly what a callback does. One thing that OOP, you have this notion of subclasses, and it seems like totally unrelated to these functional lambdas or whatever. Most of the time, when you declare a subclass of a class, though, what you're actually trying to get at is you want to override functions. What you actually are doing there in sort of an alternative way is you are defining callbacks through a subclassing. When you override those methods, it's sort of saying, I want to plug in, this is going to be on my return value, and if on event this, on event that. When I get a message, this is how you send your response back to me. That's most of what subtyping does for you in object-oriented programming languages. One big thing that functional programmers like hardcore Haskellers and MLers like to do is they like to use these they're called higher order functions. They like to use it to factor out parts of their code in sort of a similar way that a systems programmer might use dependency injection or mocks, where you want to have pluggable functionality into your code. You don't want to hard code this piece of the code accesses the database over here. You want to say access whatever the current data store. You tell the function what to do in the case that it needs to do a database access. When it's running in production, it'll access the database. When you're running your test environment, or when you're running in your test environment, it'll run off the test database. And when you're running your unit tests, it'll run off a mock rather than the actual thing. So we have lots and lots of functions, functional programming. You guys are both Lispers. You guys have got the metaprogramming and the probably some degree of metaprogramming down. I actually don't do a lot of Lisp. I sort of work on the opposite side of things with the statically typed, strongly typed languages. My primary programming language is Haskell. And so I work in this world that's very different from Lisp. And it's kind of interesting to see those two different communities side by side. In the Lisp world, you have this dynamic, everything's parentheses, everything's just a list. And you can build expressions and evaluate them, and there's macros, and you're very free and expressive to paint the world however you want, as long as you try to adhere to, there's also these other programming practices where you want to try and keep your code structured and logically organized and not be too crazy with the macros. The Haskell community is sort of like the other end of the fence. They want to try and put you in a straitjacket so you don't hurt yourself. And it sounds really terrible at first, and it kind of is. But yeah, that's the thing, is it pays dividends. When I was at Pi Ohio the other week with Carl, I came across an analogy that I really liked because we saw The Karate Kid at the hotel that we were staying at. And it was where Mr. Miyagi is teaching Daniel-san, wax on, wax off, wax on, wax off. And it's dull, and it's boring, and it's tedious, and why do I have to learn this? It's awful. But then, you just all of a sudden, as a Haskell programmer, you realize that all of this jumping through hoops to satisfy the type system, now you're an expert at karate. Not literally in karate, but you can maintain code that is in other languages unthinkable. The biggest example of this is probably the main Haskell compiler, the glorious Haskell compiler, originally the Glasgow Haskell compiler. The code base is over 20 years old. It is old code. They make regular, drastic changes to it. Like every other release, they add some crazy new type feature, and they're not afraid of breaking stuff. And a lot of that they attribute to the difficulty of the type system, because even though if you change something, you get all of these errors telling you, oh, this broke over here, that broke over there, this broke over there, and you might have to spend hours or sometimes days trying to get all of the typing errors to go away. All of those errors would have been bugs in your program had you just been allowed to compile them without a second thought. I actually just recently had an experience with this with my online IRC bot, which is written almost exclusively in Haskell. Everything else is written in Python, but most of the core language is written in Haskell. It clocks in at about 2,800 lines of code right now. I've been working on it for probably about a year, just in my spare time, whenever I feel like it. And I made a pretty major refactoring change myself, where it's an IRC bot, and I pulled all the IRC code into its own module, in the same sort of way that I was mentioning. Is sort of I decoupled it from the rest of the project using higher order functions and callbacks. And I spent probably 6 or 7 hours getting rid of all the bugs or all the type errors in this program. And when I was done, I ran the program and there was a bug in it. And I was like, oh man, that's really frustrating. And then I fixed that one bug, and I haven't found a second bug since. I probably moved the equivalent of like 500 lines of code, something like that, in one go, just to give a rough estimate. And one bug for just radical changes to this important core feature of the system that otherwise it would have taken me less time to actually make the changes, but to track down the bugs, I would be doing it for the next couple of weeks at least. So that's sort of my pitch for type safety. So, and when I say type safety, I guess I should clarify something. There's sort of these two worlds. You have your runtime and you have your compile time. And even languages that don't have a compile time, you still have a notion of what's going to work on the program immediately before it starts executing. Python can detect syntax errors. Every language can detect syntax errors. That's like the one thing that you're, maybe not Bash. maybe can Bash do that? Can it? Okay. I respect Bash just slightly more.
No, it doesn't detect them all.
Okay. Well, eventually it'll find them, but right. So the idea of a type system and statically typed programming languages is you want to front load all of the errors. When you have a typing error that prevents your program from compiling, you have a very unhappy developer. When you have a bug in your program, an error that happens at runtime, not at compile time, you have an unhappy user, which then becomes an unhappy programmer a few hours later after they find it. Or in some cases where they just kind of live with it for years and they're like, this doesn't work, and then you go back and you're like, this has never worked. Those are the best bugs. Like, you guys haven't been totally honest. You said you've been using that all the time, and you really haven't. So static type systems, there's sort of this rebellion against type systems in a lot of development nowadays. The Lisp community is obviously very against, maybe not very against. There's some schools of thought that try to add typing to Lisp. Python, they've added some very, very, very weak forms of typing. Ruby, completely, it's all runtime. JavaScript, it's entirely runtime, and it does coercion. C, again, it does a lot of coercion between types if you don't have the right compiler flags set for it. And databases tend to have these in-betweens where, like, some databases will allow you, MySQL, for example, will allow you to store I think they still do it. It's been a while since I had to worry about that. But some databases will say, you put a number in a string field. We'll just put quotes around that, and you're fine now. Whereas in Python, it's like you can't add a string to a number at all. It's like you need to be very clear. We need to know how we want to represent that number, and so you have this whole landscape of different type systems. And the one common thread among most object-oriented programming languages and their type systems, if they have any, is that they suck. They suck really, 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 really bad. They are, you don't see a lot of them. There's Java, which up until 1.5, they got this feature called generics. So before 1.5, version 1.4, if you had a list, or an array list, I think is the typical one you use. You have an array list, let's say L equals ... When you do L dot get, I think it's get 0, you get the first thing in here, and you want it to be a person object. You have person over here, person P equals that. This is going to give you an error. It's going to say, well, it's not a person, it's an object inside of there. What do you mean it's an object? I've been stuffing people in there and nothing but. Well, you put an object, it goes in as a person, but it comes out as an object. And so you have to add this stupid little cast. And there's no real type safety here. This is just something that you now have to type. It's boilerplate. It can error at runtime. It's not offering you very much safety at all. It offers you a little safety, but it's not much. And then C# just blew Java out of the water. But even beginning, I don't think it was until version like late 2s or like 3 that they got generics. And generics are where you can do this. You can do an array list of people, of person. So just scribble that in. Write that in big font so we can actually read it. An array list, so it's a list, but it's not just a list. It's a list of something. It's a list of person objects. And after Java got this functionality, everyone wanted it. Everyone who had a type system wanted a very powerful version of what this was. It's sort of the funny thing about a type system is once you realize the power that you get it and you've sort of drunk the Kool-Aid, once you're given a taste of what it's like to be cozy in that straitjacket, you want it in every language. I used to work on a language called Phantom, phantom.org. Very cool language. The original intention was the two brothers who founded it wanted to be able to compile to Java JVM bytecode and a .NET CLR intermediate representation, so they could run on both Microsoft shops and Oracle shops. The same code. That didn't quite pan out, and now it's more of a JavaScript, a JVM language that also compiles to JavaScript, and they have their own web toolkit that they created, and it works both on Swing and in the browser, which is really cool. But I was following that project for a while. One of the design decisions that they made really early on was not to include generics, except in a very limited scope, which I thought was very innovative, because they only allowed it for functions, for dictionaries, and for lists, which are the three really big ones that you want it for. And everyone complained about it, that they wanted generics everywhere. But generics are hard to do unless you start the language off with them. And that was really the first innovation of ML, and then Haskell picked it up. You have these, this polymorphism is what it's called in that world, not generics, it just goes by a different name. And I don't want to go too much into that, but it's a very powerful way of expressing languages, or expressing your programs in a way where you can put the type down, and as long as you wrote the type down, there's maybe only 1 or 2 or 3 different versions of that function that will compile. And the one that you want is one of those 3, which is great. There's actually a program, I can probably pull this up. There's a program that runs on Freenode's IRC network in the Haskell channel called Gin that allows you to type in a type signature for a function, and in most cases, it will figure out how to write that function automatically for very simple cases. And I can show you an example of that right here. So we have LambdaBot here. We've got a direct connection to him, so we can do what is the type of map. Everyone knows map from MapReduce. This is sort of Haskell notation. You don't need to really understand what it means. This says it takes a function that takes some stuff and returns some stuff. It takes a list of some stuff that you can pass into the function, and it maps that result over the function. So the map is the same map as in Google's MapReduce. But just to show you some cool stuff with this Gin feature, you can do A to B to B to C to C, and it'll actually write a function for you. In this case, it's in Haskell notation. But you can actually automatically generate a lot of functions. It's very restrictive in that sense, and very good for being able to do sanity checks on what your code does. Not to be too sidetracked on that, though. Let's see here. So why don't people actually like these type systems? Something that I should probably just sort of explain just a little bit. The type systems, by definition, are conservative. They tend to they prevent a lot of bad programs. They will save you a lot of dumb, oh, I run the code, I get a null pointer exception. That shouldn't have been the case there. And if you have these types, all of a sudden null pointer exceptions just go away. In Java and in C#, you still have to deal with null pointers, but in languages like ML and with Haskell, null pointers don't exist. Null pointers were a guy named Tony Hoare takes credit for inventing the null reference and the null reference exception that goes with it back in the AGOL language that he worked on. And he calls it his billion-dollar mistake. It's a mundane little bug that can be anything from just frustrating because it happens every couple of minutes in your code when you're trying to write it, to we didn't catch this and it's all of a sudden happening in our production system that's been running fine for the last 5 years. And all of a sudden we've just accidentally blown up our system in some catastrophic way. Those things add up, and it's probably been the biggest cause of monetary loss is the null pointer exception in programming history, all accumulated. So I made a comment here about how do you get rid of these null pointers. Everyone knows what a null pointer is. I'm guessing maybe. Null pointer? Okay, so originally when you're dealing with what language did you say again? Python. So you know the none object. So none is Haskell's version of null, and so you might have something like get person, and you pass it an ID, like a user ID, and you say p equals get person, and it gets that person from, let's say, a database. And then you want to print their name, so you do print p.name. And the problem that you're going to have in a lot of cases is you pass in an invalid ID, or their account is deactivated. Rather than throwing in an exception, because it's not really exceptional, like that person just doesn't exist in the database, or they're deactivated. That's not an error in the program, that's just data not available. So you don't want to just explode the program when their data is not available. What do you do instead? You pass none, or null in this case, which is fine, except that didn't actually fix the problem, it just deferred it, because the very next line then, if it is none, or null, you do none.name, that will crash, because none doesn't have any methods, you can't run anything on it, it doesn't have a name. And so this sort of scenario has plagued object-oriented programmers in every single language for all of time, and it's very frustrating. But the innovation in ML, which has been taken up in Haskell and Scala and in half dozen other languages, is the invention of the option type, or the maybe type. And the idea is that you have your person object, you have person P, but what you have here is this get person ID. Let's say P. Sometimes you'll write it like this: the double colon or a single colon means has type. The object P has type person. What you actually have here when you do get person ID, rather than returning a person object, you want to return this thing called a maybe person. Or it's called a option person, or a person option in ML, or a nullable, and I think C# calls it a nullable person. It basically says that person may be null, which is sort of the exact same way that the language works by default in every other language. It's this could be null, maybe it is, maybe it isn't. You have to check. The difference is that while you can call p.name on a person object, you can't call p.name on a maybe person object. You're required to go ahead and check if the function could fail and return a null value, no data available. You're required to check that before you actually call any methods on it. It basically forces you, and again, this is part of the straitjacket. It's protecting you. It's making sure that if there's a potential for this thing to fail, you must check it. There is no way to get at that person's name without first verifying it. And you typically use this pattern, or this construct, rather than using an if statement. It's called a case statement, which interacts with maybe and a bunch of other ideas from ML and Haskell in a very nice way. So you get back this let's say MP for maybe person, So you do case MP. There's two possible cases for it. It can be null, which is called nothing in Haskell. If it's null, then you have a code block over here that handles what happens if it's null. You print user not found or whatever. Or maybe you'll propagate it up to the next function and have them deal with it. You can deal with error handling the same way you would in any language. You can either handle it then, or you can have your supervisor come in and take a look at it. In the case that it's non-null, we call this a just in Haskell. We get just P. All of a sudden we have this P object which has type person. And then we can call print p.name here. Again, not Haskell notation, but close enough to get the gist of it. You can print the person out from there. And you have then, you're forced to make that check. You're forced to make sure that you've always covered your bases. Sometimes it's really obnoxious. Sometimes you just know. You're just like, I know that that's not going to be null. It's impossible for that to be null. I just put it in the database. If I pulled it back out, it can't be null. It's impossible. I have a transaction. These things don't happen. In those cases, and in most languages, even the statically typed ones, including Haskell, you're allowed to backdoor those. But when you do that, it's explicit. People in the community will be like, no, don't do that, anything but that. People do this sort of on a pretty frequent basis, though. But it makes you aware of where these sorts of errors can come in. And that's one of the biggest advantages of working in a functional language, and especially a strongly typed one. You become acutely aware of where your possible your errors are, your edge cases. Where could this function fail? And that becomes very, very noticeable to you. Even small things, you'll be looking through a Python library, and I think you guys even caught some cases there where what happens if I pass in the n that's longer than the length of the array? That's a type error. Potentially, it's hard to express in Haskell. It's possible, but you would want to be able to check for those things. You become very aware when you program in Haskell because you're able to express that in a way. The type system becomes a language that you can now think in, even when you're not working in a statically typed language. I had one more example that I wanted to show, sort of to finish up the talk here.
How much overhead is that?
The overhead for doing this sort of thing?
Just the type system in general.
So that's a good question. I'm glad you brought that up. Performance is a touchy subject. Not a touchy subject. I guess touchy among people who aren't in the functional programming community. The people who are functional programmers tend to be very optimistic about it because we have so much more information about our code in the form of static types, where we have the ability to optimize our code much more than the average person. On the flip side, though, we're also required to optimize our code because naively done functional programming will be slower. For something like this, though, there's a lot of interesting research and techniques that have gone into building these compilers. One of them that pertains to what you just asked is this notion called type erasure, which is that in languages, basically all the ML languages, which includes SML, which it's not so popular anymore, OCaml, which is so-so, F#, which is Microsoft's, check out we did ML and now everyone likes it. So you have the ML family and also the Haskell and any derivatives of Haskell as well can do this thing called type erasure, where your program has all of these types, and when it's actually compiling, a lot of these types exist during the compilation phase. But when you finally get to the very end stages of the pipeline, there's a procedure that it goes through where it actually scrubs out all of the type information. Whereas in Python, you have to keep around sort of a structure somewhere in memory that says, this object has type string, this object has type int, this object has type bool. There's none of that in a functional programming language that has type erasure. It will get rid of, I don't want to say absolutely all, but like 99.9% of all the type of information in your entire program. It's actually pretty cool in that it does that. So yeah.
About the overhead from just the writing, like lines of code from the programmer side?
From the programmer standpoint, Haskell actually tends to be, I can show you some examples as well. I stayed up all night and I wrote a lambda calculus interpreter. I cleaned it up. And it tends to be a lot terser. But
more concise, but less readable.
It can be. It's the sort of thing where you're sort of, you get to hold on to your own noose, however tight you like it, just don't hold it too tight. The language can be, you can encode it, you can play Perl golf. Everyone loves code golf. You can play golf with your code to the extent that you can with Perl, where it just looks like line noise. There's sort of an evolving standard in the Haskell community over how code should be formatted. It's nothing like Python, where there's one beautiful way to do it, and Guido van Rossum was the one who decided it all 20 years ago, and we still use it today. It's very much sort of this free-spirited, like, I like to program in this style, which is both a good and a bad thing. It can be very fun and sort of exciting to program in your own little sub-language, your DSLs if you want. But yeah, there is a danger of over-codifying that, which if you're going to be adopting the language in any sort of multi-programmer environment, you have to account for that. But on the whole, Haskell has very powerful, because of its type system, it has very powerful abstraction mechanisms. It doesn't quite go the same length that, say, Lisp would have with its macros, but it gets pretty close. You can do some really, really cool things with it, especially when you get familiar with the Haskell way of doing things, when you deal with, let's say, monads or applicatives. All of a sudden, these things which would normally become like, because you have to like indent to get these, you'd have indent, and then another indent, and then another indent, and then another indent. Once you go ahead and think about the problem, and usually with some help from the community, they sort of guide you towards what is the correct language you want to be writing this in. Not you're working in Haskell, but the sub-language. What library, what set of tools do you want to express this in? And they can get it concise and readable if you are willing to put in the time to do it. It's a little bit of an art. I'm still working on it. My code base for my IRC bot is not the nicest, but I'm getting better at it. So definitely the code length is comparable, if a little shorter, with that risk of being difficult to read. Do you have any more questions regarding that? Okay. Yeah, definitely some... The compiling phase for Haskell is sort of enormous, and there's something like 7 different stages, and then the one stage is actually a bunch of optimizations that you can turn on that probably dwarf what you can do with C code, and then hits LLVM at the end, which does all the micro optimizations of the assembly language. Just to throw one idea out there that's really cool, that you can't really do in any other language, that has to do with Haskell's complete foreboding, however you would say it. You can't have side effects in a Haskell program saved through an explicit interface, usually through monads. But there's that concept of map for MapReduce. Does everyone, we know map? You probably don't. Maybe you know map? Maybe a little bit.
I was going to ask that when you were going over anonymous function.
Mm-hmm.
If that was kind of more of a list thing, or kind of, I always think of it as a functional stalwart kind of deal.
MAMP is sort of like the umbrella of all functional programming, I think. It's the one thing that everyone shares is map. So what map does is it takes a function. Again, it's a higher order function. You pass it a function, and you give it a list. Maybe it's A1, A2, ... However many elements you have in your list. And what this will reduce to is F A1, comma, F A2, ... F, your last one. So it will take that function and just spit it all across your array and hit every single one of those. It's the cornerstone of Google's MapReduce, which is they take these are all the web pages in the world, like all of them, literally. They don't do all of them, but a large section of their day's data. They take some function, which is, let's say, a valuation. It says, how relevant is this? It takes a page as input, and it gives you back a 5-star rating. Whatever, 1 star, 2 star, 3 star, 4 star, 5 star, however they want to do it, however they want to represent it. What this will do, you hit it with map, and all of a sudden you have a rating for every single website in the world. And then the next thing you want to do is something, some kind of reduce operation where you take that information and you gather it up into a nice number, and you say, the internet is really awesome today, or I don't know exactly what they do it with, but it's very easy to parallelize and because it's all pure, because it's referentially transparent, it's very easy to take these things, throw them on different computers, and it doesn't matter because it's all pure code, all working on immutable data. But why did I bring this up? I was going to bring this up for a reason. Oh, the cool thing I remember what to bring up now. There's this sort of tendency. A map also works like a very specific kind of for loop. I want to loop over all this data and apply a transformation to each thing in there, and then I'll do something with that data eventually. Sometimes you want to loop through and apply one transformation, and then you want to loop through and apply a different transformation. And the way you do that is you want to map a function g. What list do you want to do it to? Well, whatever the result is, mapping a function f. Naively, just if you were to compile it directly and literally apply each of these functions in turn, you'd take this function f and you'd go through each element of the list, every website on the entire internet, and you'd apply f. So you've gone through the list once. And then you'd do it again with a different function. You go through the list twice. That's really inefficient, right? You don't want to go through the list twice. You could just apply both functions at the same time. But then maybe you'll sacrifice something in terms of code readability or modularity of your code. But with the Haskell compiler in particular, you can do cool things like this, where you just write this code. This is the code that you write. And the compiler will automatically sort of translate that into map g compose f, where this compose is, if you remember it from 7th grade algebra, it's the function that you apply f, and then you immediately apply g afterwards. But the thing to note here is that you only map once, calling that one function. And that's an optimization that happens automatically for you a lot of the time, and it's magical and wonderful when it happens. And very frustrating when it doesn't quite happen when you expect it to. But when it does work, it makes your code go much faster than it should go if it were just naively compiled. This is a technique called deforestation, or stream fusion, where you take going through a stream twice and you just go through it once with the sort of iterated or the composed functions. So there's one more thing I wanted to present, which is just a little more about the type world. And this I can actually probably just show on the screen. This is actually an example that I got from, I can't remember his name. Yaron Minsky. He's got 2 videos on YouTube that are done in OCaml. He works for, I think it's Jane Street, which is a stock exchange trading company, I believe. And he does some really cool talks that are on functional programming. Because I don't really know OCaml so well, and I don't really like the syntax as well as the Haskell, and I sort of rephrased it. The ideas translate almost perfectly, though. So I want to talk about these things called disjoint union types. And to start with disjoint unions, we want to talk about product types. These are also called sum types, variant types. There's a bunch of names for these things. We're going to start off with the Java example. You have a class, and then you have some number of fields. We'll just say it's those 3 fields. And what that means is that a person object has a name and an age and maybe some cats. I guess there's only 2 ands because there's three different options. Well, what about or? What if I don't want to have, I mean, in this case it makes sense to have and. Are there data structures, are there classes, are there types where we want to have or? And because I don't have slides, you can see the answer is yes. You have day. Day is an enumeration type. I can have when you have a day, it can either be Sunday or Monday or Tuesday or Wednesday. The vertical bar there means or, sort of like international computer science speak for the word or. But enumerations are allowed in a lot of different languages. Even like I think Python got them recently. Java got them in relative history. But we can do something that's slightly fancier than an enumeration type. And so this is an example that I stole from Yaren's video. Very good videos if you're curious about it. He's very well spoken and talks from a very pragmatic standpoint. He had this example I didn't put the Java code here. Oh, well, I messed it up. He had this example of working in his environment. He wants to represent something that he would have to deal with on a regular basis, which would be a connection to some database or some transaction service. And so down here you have the naive implementation of how it would look. This is basically what it would look like if you took a Java programmer and had him work in ML. And he presents this and then sort of elaborates on it and explains a slightly better way to do it and sort of justifies it. So connection info, we want to connect to a server somewhere in the world, maybe some stock exchange server. And when you connect to something, you keep some information about it. You keep the state, and the state can be any of these. This is just an enumeration again. Your state can be disconnected, in the process of connecting, or totally connected. And then you also have this other information. This is and. You have a state, you have the internet address, the IP address of the server you're connecting to. Once you're connected, you can have a timestamp for the last time you pinged the server to make sure that it's still, the server connection is still alive. You also have the last ping ID, so you can keep track of what was the last ID that you saw. Because we only have those in the connected state, though, these are going to be maybes. This means nullable. These could potentially be null because when we're in the disconnected state and when we're in the connecting state, those can't be set. Once we're connected, we're also going to have a session ID. When we're connecting and when we're connected, in these two cases, we're going to have a timestamp which will tell us when we started the connection. And that's handy to keep around for when you want to keep track of timeouts or something like that or diagnose issues. And then in the case that you get disconnected or that you purposefully disconnect from the server, you keep a timestamp of when that happened. And this works perfectly fine. This is how a Java programmer would write it. This code would work just as well as Java. And his talk, he gives this as an example of something that this is pretty good. We can actually do better if we just change the types around to take advantage of the so-called invariance of this data type. What do I mean by invariance? I mean there are certain things that are sort of implicit in the structure of this data. The last ping time and last ping ID, these are only going to be available when the socket is connected. In the other two states, they have to be null. In any case where you see one of them is null and the other one is non-null, you've made a mistake. You have an issue. Because that means that at some point, a programmer tried to set the state and then forgot to fix the other one to be the same way. There's a bug in the program. So these are both only available when connected, and they're both unavailable. They're both null when it's disconnected or in the process of connecting. Session ID is also only available when you're connected. When initiated, I guess this is only available when you're in the process of connecting. Once you're connected, you want to set that back to null. And if you're disconnected, you want it back to null. And when disconnected, you only want that to be shown if you've actually disconnected. If it shows, if you've just created a new connection and you're connecting, and all of a sudden that shows disconnected, you've got a bug in your program. So there's these requirements on this type that are sort of non-obvious, and well, if you think about them, it works. But if you're modifying code and you're not, you're tired and hungry and you want to go home, you just want the code, and if you're fighting the type system, you just want it to compile, there's potential for there to be bugs in this. And so what he does is he refactors the code to look more like this. And I have a link to his video if anyone wants to see this. Starting at the bottom here rather than at the top, I think makes more sense. We've basically taken those fields and pulled them out where they don't make sense. In cases where they have to be null, we can leave those fields out. And in cases where those fields have to be set, we don't make them maybe types. You can see that out of all of the different types, we only have one maybe left. Everything else has become a concrete data type. There's no possibility for it to be null. Down here in the connection info, we still have that state. Connecting, connected, disconnected. And the server address is always going to be there, regardless of what state we're in. When we create the object, we need to know where we're attempting to connect to, where we're thinking about connecting to, even if we aren't connected. The connection state actually contains these three guys. These guys are the same three statuses that we had before. It's the enumeration, but in addition to having just I am disconnected, I am connected, we also have some additional data that's associated with each different state. In the case of connecting, we have this thing called connected details. So this state, this connecting details, is only available when we're getting ready to connect to the database. Connecting details, when initiated. It's not going to be nullable, so it has to exist. And so when we're connecting to something, when we're in the process of connecting, we know that there's always going to be a when initiated, and it can't be null. So we've eliminated that null pointer possibility from our world. We've also eliminated the possibility of there being a last ping ID or a session ID. There's no way that you can have a stale session ID from the last time you connected, because there's that data can't be stored there. It's just not available when you're in that mode. A similar thing happens in your connected state once you're actually connected to a server. You have the last ping ID, which is maybe. So you can have, these can be nullable. One thing that he's done here is he's taken advantage of the fact that ML in his case and Haskell in this, in my version of it, has tuple types. So you have a pair, and the maybe applies to the pair. That means you don't have a timestamp that can be null and an integer that can be null. You have a pair that can either be null or it can be both. Null or both. Null or both. You can't have null and yeah, or yeah, null. It has to be both are unavailable or both are available. And then the session ID is always going to be required in that state. And then finally we have very straightforward, the disconnected has, I made a typo here, this should be disconnected details. The disconnected, when you're disconnected, you have a disconnected timestamp, and at no other time do you have one. Once you start reconnecting, that timestamp is no longer available to you, it goes away. So this is an example where I can run it or anything, but you can see just by looking at the fact that we have fewer maybes, which are the nullable types. There are fewer possibilities for null pointer exceptions. We've saved just a small fraction of that $1 billion that we've lost, plus accumulation since the time when he made that statement, which was like a decade ago or so. We have this interesting way of looking at data types that we didn't have before. These are called algebraic data types, and they are sort of the cornerstone of these ML Haskell languages, also available in Scala and to lesser degrees in Python and in Erlang and other languages. Lisp as well, I believe, usually has some way to work with some kind of data types in this way where you have structured data types. So, do I have anything else? Oh, that's the end of my talk, I guess. So,
Thank you.
yep, thanks for attending.